Okay, now, so far you have been mainly dealing with how to obtain differential equations. Now, once we have learned how to obtain the differential equations, then we will do something with it. Obviously, we need to solve them. Now, what we have obtained so far can be expressed in this form. There are a few variables, the state variables, normally these are defined as the minimum number of coordinates that you need in order to specify the dynamical status of a system uniquely. So, these are the state variables, and you have also understood that normally the positions and the momenta of the masses would form the state variables, or in electrical circuits the charge across the capacitors which are equivalent to the position variables, and the current to the inductors which are equivalent to the momentum variables or proportional to, these would be the state variables. So, there would be a momentum associated with an inductor, there will be a position associated with the capacitor, and these would be the state variables. So, you have got the state variables, say these are x 1, x 2, x 3 and all that. Then what we have done so far amounts to saying that we have obtained x 1 dot is equal to some function of x 1, x 2, x 3 to x n. Similarly, x 2 dot is equal to another function of x 1, x 2, x 3 to x n, so on and so forth. X n dot is equal to so that is what we have done so far. In brief, if you express that in a compact matrix form, you would say x, capital X representing this whole vector dot is equal to some function of capital X. So, this is what we have obtained so far, and then the next task is to solve it. Now, if the right hand side all these are linear, that means this is a linear combination of x 1, x 2, x 3 and x n and all that. In that case, the right hand side is expressible in a nice matrix form, and remember, whenever you did obtain that kind of a equation with the right hand side in a linear form, you should always express in the matrix form in the answers. Now, when that is true, then the solution of this equation would be obtainable easily from in a analytical manner. We will deal with that, but mostly you have also noticed that this side is not expressible in a linear form. In that case, the numerical technique is all that we have in hand. But notice that here, even though you may have attended some classes on the numerical techniques, I will briefly only in one class cover the essentials of the numerical techniques, so that the whole thing is complete. Now, what these define is something like this. Suppose, okay, after we have defined this, the next conceptual step is to define a space in which the x 1, x 2, x 3 and all that, these are the coordinates. That would be state space. So, since we are constrained to draw and think on a 2-dimensional paper, so I will use a 2-dimensional state space to illustrate what I mean. You have say x 1 and x 2. What these differential equations actually specify is that, say if my point is here, which means that now that system has a specific value of x 1 and a specific value of x 2. In that case, what would this say? It says that x 1 dot is a specific function of x 1 and x 2, which means I will write it here, x 1 dot is equal to f specific function of x 1 and x 2, which means that if x 1 and x 2 are known, then x 1 dot is known. X 1 dot means how would x 1 change in the next instant. So, that is sort of something like this. Okay. Similarly, the equation x 2 dot is equal to another function of x 1 and x 2 will give this, not only in the direction, because x 1 dot means how does x 1 change with time, it could be this way or that way, and its magnitude will be given by the length of this vector. So, from this you could infer that in the next instant it would move in this direction in the state space, right. So, what effectively the differential equation has given is this vector in the state space. Similarly, if the point is here, it would give another vector in the state space, meaning that if the point is here, it will move in that direction. So, notice then that this set of differential equations actually define a vector at every point in the state space, right. And say there is a set of vectors like this, and it is not difficult to see that if you have a initial condition say here, it would more or less follow the stream of these vectors. So, anything that we try to think up regarding the solution of the differential equations either numerically or analytically should follow this conceptual issue that it would follow the vectors. It is like a flow, it is like a flow that is going, and if you drop a particle somewhere in the flow, it moves with the flow. So, that is what we are trying to find out. That is why the set of differential equations is also called a flow. In literature, you will find that these word flow and a set of differential equations are being used interchangeably. The conceptual issue is this, that a set of differential equations actually define a flow. So, now you have a initial condition, and the solution of differential equation would essentially means how it moves with the flow for a given time. Okay. Now, how to do that? So, in that case you would get some kind of a movement in the state space, but you could say no, I am interested in mainly how it changes with time, say how x 1 changes with time and how x 2 changes with time. In that case you will get a waveform something like this, say this is your time and this is your x 1. So, for every value of time you get a value of x 1, that is the solution of the differential equation. Similarly, you have another solution for say time, this x 2. These put together, that means if you forget now about the time, rather you are more interested in how the point state moves in the state space, then you would plot x 1 versus x 2, and that is what I have drawn here. Okay. So, now we will deal with this issue analytically later, but first let us find out how to obtain the numerical solution. You might say fine, what I will do is at every point I will find out the direction of the vector, which you can do the moment you have it, and then I will take a step from here to here along that direction. I come to this point, at this point again I evaluate the right hand side and I again draw the vector, and so on and so forth I draw. Yes, that is the simple thing that you can do, and that is what is actually done in many cases. The only problem is that in that case how big a step do you take, and there is obviously the underlying assumption that while you take this step from here to here, the vector actually does not change. So, you have tacitly made that assumption that in that step length the vector does not change much, but it could. So, this method would incur some error, and we need to do some approximation in order to do better, and that is what all the numerical techniques are all about. So, in concept what are you doing? We are taking the steps, trying to make sure that we are along the vector as close as possible. So, let us start with considering a one dimensional differential equation. That will be easier to start with, and then we can continue to higher dimensions. So, we are considering say x dot is equal to some function of x 1d, that is simple. And what we are trying to do is to plot against time the value of x, which would be actually continuous line, but we will not be able to obtain a continuous line because we are taking finite steps, and therefore, we will say that at the 0 time it was say here, and then we will this will tell us how does x change with time, and therefore, along that we take the next step, say at this point we come here, then at this point again we calculate the right hand side, take the next step, say we come here, take the next step we come here, take the next step we come here, say this way we can proceed. But actually we are calculating in steps, and this step length say is your h. So, if you say that if you let the initial value say x at 0 is equal to say x naught, then x 1 is what? X 1 is this one, this is x 0, this is x 1, this is x 2, x 3 and all that. So, x 1 is equal to x naught plus ideally you would like to do the integral, integral of starting from t 0, sorry this would be t 0 at t 0 to t 1 f x, this is what you want to do. But then this is not known, and that is why you needed to take a step, that is why you needed to make an assumption or approximation, and the approximation was that this slope that was calculated at this point remains the same till this point. Okay. So, with approximation then we would say that x 1 is equal to x naught plus h f of it is actually I should say also dependent on time. So, it is not only dependent on x, but it is also dependent on time. So, f of this is x naught and t naught. Okay. So, at t naught whatever was the x naught, f is calculated on the basis of that times h, the time is what you have to add to the original value. Similarly, x 2 is equal to x 1 plus h f x 1 sorry t 1, and then you continue this, you have x n is equal to x n minus 1 plus h times f x n minus 1 t n minus 1.
Sir, in the integral you have written dx.
Oops. Yes, you are right. Sorry, this will be t, obviously not differential. This is x t, is dependent on t, and then you integrate over t. Okay, so this is how you calculate the different steps, and this method with the first approximation is called the Euler method. So, this is the Euler method. Let us illustrate this with the help of one simple example. Say your x dot is equal to sin x plus x square. Say at t is equal to 0, x naught is equal to 1.0, okay, and say h is equal to 0.1. Then how would you calculate the first step? Start x naught is equal to 1.0 we have known, x 1 is equal to, how do you calculate that? X naught plus, so 1 plus h times f calculated at the initial condition, h is 0.1 times this thing sin x was sin 1 plus 1 square, right, that comes out to be. So, you have got the numerical value 1.184. X 2 is equal to this plus 1.184 plus 0.1 into sin 1.184 plus 1.184 square is equal to 1.4169, and so on and so forth. You can continue. X 3, I will write x 3 because we will compare with the other methods also. 1.4169 plus 0.1 times sin 1.4169 plus 1.4169 square is equal to 1.7166. So, and so on and so forth. We are taking steps exactly like this. Okay. So, this is how you would calculate by the Euler method. Now, it is clear that in the Euler method at every step the errors will build up, and naturally when you are calculating x 2, you are putting the result of the x 1 in here and all that, and therefore, if there is an error it will build up in the next step, it will build up in the next step, and therefore, there is a possibility that will blow off. In order to avoid that, you would need to make the h as small as possible. The moment you make very small h, the computation becomes very slow. So, we need to do something better. In the next step of the assumption, we can say that, say we are now this is t, this is x, we are now say here, and in some way suppose you know that at x 1 you are here. So, what way I will come to that later. So, this is the t 1 time, this is the t 0 time. Then the next approximation is that, what was our initial guess? It was that the slope remains the same from this point to this point. Now, this slope will still assume that it remains the same, but will sort of improve upon the value of the slope. What can we say? We will say we will not take the value here, rather we will take the value somewhere in between. So, in that case our solution at x 1 becomes, x 1 will become x naught plus this is the total h, this is h by 2 times, then we have to take the average, it is f of x naught t naught, this one, plus f of x 1 t 1, right. So, what have we taken? The slope at this point and this slope at this point we have taken divided by 2. So, it is a average of the two. So, we have taken the average slope, but still the question remains, how do you know this? Because you have not yet reached here. So, you do not know this. Yes, then the nice thing is that you have the earlier calculation based on the Euler method. So, which you can substitute here. That was approximate, all right. So, this will be approximate, all right, but ultimately this will be a little better approximation than what it was earlier. So, you substitute it here. So, we have x naught plus h by 2, it would be f of x naught t naught plus this whole thing f of x 1 was x naught plus h f x naught t naught comma t 1. Okay. Normally, when we write this, we try to abbreviate so that the right hand side can be expressed in a more compact form. Then we say k 1 is equal to h f naught. F naught is f calculated at x naught, and k 1 is h f of x naught plus k 1 comma t naught plus h. So, if you define this, then we can simply write on in terms of that x 1 is equal to x naught plus half k 1 plus k 2. So, this term is k 1, this term is k 2. So, we have x naught plus half k 1 plus k 2. Okay. So, then this is the next step of better approximation. So, what have we done? We first said that we will take the improve upon the slope that you take constant between this point and this point, and in order to improve upon, we said that earlier we had taken this slope to be constant at up to this point. Now, we will say that no, the slope here is constant from this point to this point, obviously better approximation. And then in order to do that, we wrote it this way: the slope is then this slope, this plus this by 2. So, you have a better approximation. Then we substituted from the Euler method whatever was this value, and then we wrote it separately this way. This part is this part is this.
So the second equation should be k2 is equal to
Sorry, k2 is equal to. Fine. So, ultimately you have this. Now, this is called the trapezoidal. Trapezoidal means what we have done is essentially say that it is a trapezoid, and then we have taken the middle point. Let us illustrate the same problem that we did earlier on the basis of the trapezoidal rule. Our problem was x dot is equal to sin x plus x square, and our x naught was 1.0, h was 0.1. We now calculate with the help of the trapezoidal rule. What will we say? We will say that when calculating x 1, we need to calculate k 1, and the k 1 is exactly the same as whatever we have calculated earlier. So, no, this part, not 1 plus. Where is it? Where did you keep it? Here. H times f naught. F naught is only this part. So, it will be 0.1 times sin 1 plus 1 square is equal to 0.184. Okay. K 2 is this substituted here, 0.1 times sin 0 no, not 0, 1.184 plus 1.184 square is equal to this. Again we have calculated, it is 0.2328. Okay. Once we have calculated this, we can substitute in this equation to obtain x 1. X 1 is then x naught was 1.0 plus half k 1 plus k 2 is 0.184 plus 0.2328 is equal to 1.2084. Where is the calculation last time? Yes. See, in the Euler method, at the end of x 1 we had calculated 1.184, while by using the trapezoidal rule we have found x 1 is equal to 1.2084, which is a better approximation than the earlier step. Similarly, your x 2, in order to calculate x 2, go to the next step, then we have to calculate it again. Next step, again k 1 is equal to 0.1 times. Now, this has to be substituted. It is sine 1.2084 plus 1.2084 square is equal to 0.23952. K 2, how do you calculate K 2? How do you calculate K 2? Yes. Yes. So, you have to calculate the f at the next instant. So, it is 0.1 times sine, it would be 1.44792 plus 1.44792 square is equal to 0.30889. Once you have done this, you can calculate x 2 is equal to x 1 1.2084 plus now half of k 1 plus k 2 0.23952 plus 0.30889 is equal to 1.482605. Now, you notice that how much is it better than the last calculation? This was calculated on the basis of the Euler method 1.4169, where in this case x 2 is equal to 1.482605. Obviously, that is a better approximation, but still it is an approximation. Now, it so happens that in this method you have still errors, but the error scale as h cube. Fine. So, you have learned the trapezoidal rule also. Yeah.
So in the last part, from where did we substitute the value 1.44792?
What did you calculate? That is, where did we get it from? Yes, x 1 plus k 1. So, if you do that, you get this. Okay. Now, you notice that we are going into successive stages of better and better approximation. The first was the Euler method, which is also called the first order approximation. Second was the trapezoidal rule, that is called the second order approximation, and then you can easily imagine that we can make third order, fourth order, fifth order approximations. Okay. Because what was the logic? In the trapezoidal rule we said that this point will be approximated by the first order approximation. In the next stage you can say no, this point will be approximated by the second order approximation, and therefore the midpoint again will become a better approximation. A fourth order approximation would be this point will be calculated by the third order approximation, and then the slope will be approximated in the fourth order. Okay. Thereby you can go on increasing the accuracy of the approximation. And this whole logic was laid out by two people, Runge and Kutta. So, the whole logic is called the Runge-Kutta method. German, therefore, U would be pronounced as U. So, it is not Kutta, it is Runge and Kutta. That is why the Euler method is also called the first order Runge-Kutta method. The trapezoidal rule is also called the second order Runge-Kutta method, and naturally you can easily imagine how the third order Runge-Kutta method would look, fourth order Runge-Kutta method would look, and fifth order Runge-Kutta method would look, and so on and so forth. And in fact, all these are used, but once you understand the conceptual clarity, with conceptual clarity how you progress in the order of approximation, you can, the whole thing falls in place. Out of all the various things, what is most commonly used is the fourth order approximation. So, without giving the details which you can find in any numerical analysis textbook, we let us just write down the steps in the fourth order Runge-Kutta method. In that case, the x 1 will be x naught plus some things, that will be 1/6 of k 1 plus twice k 2 plus twice k 3 plus k 4, where k 1 is equal to the first one, obviously, h f x naught t naught. K 2 will be h f x naught plus half k 1 t naught plus half h. K 1 is known, so you can substitute it here, h is known, so you can substitute here, and you can evaluate the function, therefore, K 2 will be known. K 3 will be h f x naught plus half k 2 t naught plus half h, and K 4 will be h f of x naught plus k 3 and t naught plus h. Okay. So, once you have calculated this you can substitute it here and you can get the first step. Then the second step is all these exactly the same, only in place of x naught you substitute x 1 and so on and so forth. So, let us just illustrate one of these calculations. We will still keep these in hand so that we can compare. Still we are going with the same equation, x dot is equal to sin x plus x square. We know that our x naught is equal to 1.0, h is equal to 0.1. So, we first calculate the k 1. K 1 is what we already did. So, that would be 0.1, yeah, we have done it, just let me write so that we can write in the same style. Sine 1 plus 1 square is equal to 0.18. I'll write it to higher decimal places, 141. Then your K2 will be 0.1 h f of x naught plus half k1. So, x naught plus calculated at that particular point, it would be sine. Now, just calculate what is x naught was 1.0 plus half of this, it would be 1.09071 plus 1.09071 square is equal to 0.20766. Okay. 18. Then this should not be there. 184. Sorry. Okay. Now you have K3, which will be h times f of x naught plus half K2. K2 is now known. Substitute it here. You get what? 0.1 times sine of what? X naught plus half of this. It will
change sine 1.092 plus that is 0.184.
Oh, this one was calculated on the basis of with 1, no? Can you just check with a calculator whether the mistake was here or here? Because I had done the calculation once, which one of these steps may have been mistaken, or I may have written it wrongly. Whether this is correct or this is correct.
This one is correct.
This one is correct.
So 1.18414. Previous ones are all correct.
18414. Okay. So what is the result of this step then?
Sine 1 point, not over here will be sine 1.092.
092.
0.0.
Okay, 92. I'll stop it here. 92, and this one would be 092 square. Can you tell me what is the right hand side? 0.20800. 0.20800. Good. So now K3 will be calculated with sine 1 plus half of this. How much is that? Plus 1.104 square is equal to it should be 0.21 something, right? How much does it come to be? 1? That's okay. And your K4 is 0.1 times K4 is x naught plus K3. So we can directly add this sine 1.211183 plus 1.211183 square is equal to 0.2402989. Okay, fine. So, we have calculated the case. Now, your x 1 will be x naught 1 plus 1/6 of k 1, which is 1.1841 plus twice into 0.208 plus which one? Oh, sorry, is 0.1841 plus 2 into 0.208 plus 2 into 0.211183 plus K4 is 0.240 is 3 maybe approximately. So, this comes to, that will end the story. Anyway, you are able to calculate. So, let us not drag with it. 1.21044. You notice that that calculation is definitely better than the first approximation that we did. It is also better than the second approximation. Where is it? X 1 is here. Second approximation that we did. Now, it is rather simple to write down a program to proceed this way. So, you should all have to do that. That means, that will be an assignment. But let us first understand how to extend this to higher dimensions. We have done it in 1D. If it is a 2-dimensional system, exactly the same logic works, but independently in the 2 directions. So, it will be, suppose you have the equations given as x dot is equal to some function f and g, right, it will be easier, x, y on time, y dot is equal to another function of x, y and time. In that case, your x 1 will be x naught plus 1/6 of k 1 plus twice k 2 plus twice k 3 plus k 4, and y 1 will be exactly in the similar way plus 1/6 of another function, we will say L 1 plus twice L 2 plus twice L 3 plus L 4. Okay. And these will have to be calculated exactly the same way. For example, K 1 will be what was it, H f. Now, this only thing is that it has to be calculated x naught, y naught and t naught. L 1 is H g of x naught, y naught, t naught. The next step, K 2 is H f of x naught plus K 1 by 2. This has to be also written in terms of the y naught plus L 1 by 2 t naught plus h by 2. Okay. So, the conceptual change is that while you are changing this, the y has to also be changed to the next step. Similarly, L 2 is equal to h f h g x naught plus k 1 by 2 y naught plus L 1 by 2 t naught plus h by 2. Okay. Next step goes in exactly the same way. Fine. The result of all this is that if you write down the solution programs, and started with some initial condition, then you would be able to get a result file that will be the T naught and the x naught, T 1, x 1, not only that, y naught, y 1, T 2, x 2, y 2, and so on and so forth. 3 columns, if it is a 2-dimensional system, you get 3 columns. So, as the time progresses, how does x change, how does y change, and then you would be able to plot it like t versus x, some kind of a waveform, y versus t, again some kind of a waveform. Not only that, also x versus y, some kind of a, not a waveform, but its movement in the state space. So, your assignment will be to write the solution program in 4th order Runge-Kutta method, not the others, not necessary, because they are relatively less accurate than the 4th order. 4th order is accurate to the extent of h to the power 5. So, it is more accurate. And then you will have to solve any one of the problems that I gave you in the tutorials. For example, you have written down the code for written down the solution of the inverted pendulum, you have done it for the double pendulum, the one that was like this. Any one you take and obtain the solution starting from some initial condition. Here the initial condition would be some initial position and the momentum of these 2 masses. Okay. You have written down the solutions already as part of the tutorial, and for the part of this assignment you will have to obtain the solution. Let us, for the sake of uniformity, do not take just any, but do this for this system. You have all done it as a part of your assignment earlier. Now, you obtain this solution starting from some initial condition. Okay. Now, the additional nicety that one does is, normally if you write the differential equations and then try to solve it, one sets the h something a small value, something like this. But then this h may not be sufficient where, for example, okay, imagine that you are taking the step length like this and you are calculating. So, if it is going like this, then the amount of approximation that would be involved in going from here to here, here to here, here to here, even if that approximation is accurate to the h to the power 5 extent, that is reasonably good. But suppose it is like something like this and you are taking the steps like this, then what? If the solution has sharp turns, obviously this will incur error still. The other problem is that in order to avoid incurring that error, you might say that no, I will then change it to 0.001. Fine, you will be better off, but then the program will be 10 times slower. That is why one needs to strike some kind of a compromise, and the compromise is often not available a priori. You have calculated it, you have got an orbit, and you never know if it is correct. So, that is a typical problem in solving the differential equations. Now, given a specific problem, you should be able to see whether you are likely to encounter this kind of situations. When are you likely to encounter? That is what I referred to in the last class as stiff systems. Stiff systems are where there are completely different time scales within the system. Something is oscillating say at megahertz frequency and something else is oscillating say at hertz frequency, then you have trouble, because something is really oscillating very fast and therefore, your program should be tuned to that frequency. That means, the h step will be so small as to be able to see those oscillations also. But if you set the h larger, then you will be completely missing those oscillations. If you try to capture the oscillations, the program will be horribly slow and you will not be able to proceed much. It may so happen that some system is more or less smoothly proceeding, so that you are happy, but at some point it takes a turn. While it is smoothly proceeding like this, you never know that it is going to encounter a turn. So, something has to be done, something has to be built into the routine program, so that you can find out that yes, I am encountering a problem, so I need to reduce my step size. And that is why most of the modern programs for the Runge-Kutta solution incorporate some kind of a variable step size routine. The variable step size routine is where, depending on the character of the solution, you vary the step size. Where it is going smoothly in a more or less linear fashion, you make it large, so that it calculates faster. But wherever it is something like this, you make it small. How do you know? The nice way to know is that we have already talked about the second order, third order, fourth order, fifth order Runge-Kutta methods. So, supposing you have started here and you are trying to find out whether before the next step there is going to be a turn. Where will that be manifested? It will be manifested in the calculated value of x1 if you calculate by the Euler method, by the trapezoidal rule, by the Runge-Kutta method, the values will be widely different. Okay. But if it is more or less smooth or linear, then they will be more or less the same. So, what one does is, normally you set a tolerance and then calculate it for with the third order Runge-Kutta method as well as the fourth order Runge-Kutta method. If the difference is beyond the tolerance limit, then you make the h say half, because that has detected no, there is a turn. So, you make it half and then do the same thing once again. When it goes below the tolerance limit, use that value of h and calculate. But it has to be again dynamically done, so that before the next step, if you find that no, it is below the tolerance limit, increase it till it still remains below the tolerance limit, so that when it goes like this, you should be able to calculate with a larger time step. In your program, incorporate that also. Because otherwise, for practical systems, your program will not be able to execute properly. Clear? Incorporate that also. You would notice, if you look at the MATLAB's code, MATLAB's solution of differential equations are given in two types of ODEs, two ODE solutions. One is called ODE 2.3 or ODE 3.4 and ODE 4.5. What does it mean? It calculates it by the, suppose ODE 4.5, it means that it calculates by ODE 4, Runge-Kutta fourth order method, the next step, also calculates by the Runge-Kutta fifth order method, the next step, compares with the tolerance, and then does the variable time scale algorithm. You have to incorporate the same thing. Clear? So, that is how you would write the program as the assignment to be done over the next weekend. Clear? Fine, that is all for today.